All right, so we've got a little bit of time left. I want to get us at least started into chapter 14. Now, chapter 14 is our last chapter in this textbook. There are other chapters that we did not get to, we will not get to. Some of them are pretty interesting. We never really fully talked about explosives. There's a lot of interesting stuff in there about explosives, and you can kind of start to put together some of the pieces of the things that we've talked about up until this point. But we're going to end with polymers because, again, in terms of commonality, polymers are a big part of our everyday existence. You're sitting on a polymer right now. The table that you are writing on, also a polymer. There are lots of polymeric materials. We are wearing polymeric materials right now. So an investigation of polymers is kind of necessary because, again, of their common nature. So what is a polymer? Well, if we're looking at kind of the big picture definition of a polymer, we are talking about something called a macromolecule. Macro meaning large, large molecule. So while most of the things that we have discussed thus far have had relative masses in the tens and hundreds of grams, macromolecules tend to have molar masses in the thousands and 10,000s of grams per unit. That's how big we're talking about here. Now, how do we get to this state? How do we create these macromolecules? That's one of the things that we're going to be talking about. What we have to understand, though, is that when we look at these polymer macromolecules like this, we're looking at hundreds or thousands of repeating units. That's what makes a polymer a polymer. We're going to have some sort of compound. That compound might be relatively small in its overall size. So kind of the most common one, ethylene. Ethylene is C2H4. Its total mass is about 28 grams for every unit. But yet, when these ethylene units come together and just link up, one after another, after another, after another, after another, after another, they create these big molecules that have thousands of these ethylenes lined up one by one by one by one by one. And each unit takes that mass of 28 times 1,000 units. That's a 28,000 gram unit. That's gigantic. Now, within polymers, there are different kinds. There are what are called thermoplastic polymers. These are ones that when we heat them up, they can soften. When they're in their softer state, we can mold them into a particular shape or a design. And when we cool them down, they'll just harden back up. But they'll keep whatever shape we put them in. There are also thermosetting polymers. Thermosetting polymers are, once we have molded them and let them cool down, we cannot reheat them and get them to form new stuff. Those common examples of these are your order style plastics. You have any of those reusable water bottles that are made out of plastic. That Nalgene material, that's a thermosetting polymer. They mold it into the shape of the bottle, it cools, and now it's as hard as a rock. Makes it a great water bottle. Hard to break it, hard to shatter it. But as far as the polymer goes, it has a single use in terms of you can't reform it into something else. Because of their makeup and what goes into them, most of these molecules, because they are carbon and hydrogen based, they will burn. And when they burn, they will generate toxic gases as they do. The primary reason for that is because, again, what they're made out of. If it's just carbon and hydrogen, they're usually okay. You start throwing in chlorine atoms or cyanide ions, and now you got a whole different set of problems. And because they are so common in all of our commercial and consumer goods, polymers are involved in almost every fire. You've got something on fire, there's a good chance of polymers involved. Especially if we are talking about a house fire. Now we can classify polymers also based upon their use. The most common polymers are plastics and fibers. In plastics, we're talking about polymers that we can shape. We all have a general understanding of what a plastic is, what it looks like. The connotation behind the name plastic, meaning we can kind of get it to form whatever shape that we want. So we can form it into tubes, we can form it into bottles, we can form it into cups, we can form it into chairs, we can do lots of things with them. Now, depending upon the polymer type, we may or may not be able to reset them again. Most of them are thermo setting. Polymers can also be drawn into fibers, things like threads and yarns. These can be both natural, like wool, cotton, silk. They can also be artificial, like polyester, Kevlar, Nomex. Most of these polymers start out in the thread or yarn stage, but are very easily woven together to make fabrics and textiles. There is a third category. That third category is the elastomer. Elastomers are polymers that have a very particular property to them. They have the ability to be stretched. So you take a piece of plastic and you try to pull it apart, you don't get very far. And if you are able to elongate it in any kind of way, it's stuck that way. It doesn't snap back into position. But with elastomers, what we see is that their molecular structure is such, they're usually coiled in some kind of way. So think about stretching out a spring. You take a slinky and you stretch it out. Well, when you let go of it, when you remove the stress of you stretching it, it snaps back to where it was. That's kind of how elastomer is structured on the molecular level. So because of that, because it is coiled up, we can stretch it out, but we can also watch, and when we release that stress, when we stop stretching it, it'll go back to where it was. You're familiar with some of these. Spandex, nylon, stretchy material, rubbers to some degree. How do we get these? Well, the formation of polymers comes from a process called polymerization. A polymerization reaction comes from the reaction of the repeating unit The repeating unit is called a monomer. And what happens is that monomer itself might be pretty reactive. That monomer itself might be kind of dangerous on its own. But if we introduce the right substance to it, we can get that monomer to basically unravel itself. So that's what's called an induction molecule, or an induction phase of polymerization. We take that monomer, we introduce some sort of induction substance to it, and that induction substance causes the monomer to start to link together. Starts causing the electrons inside of the bonds of that monomer to go crazy and start just dishing themselves out and forming bonds. And that process of forming all these extra bonds will usually end up in the formation of a polymer. And it'll continue until one of two things happen. Either we introduce some kind of agent that can stop the induction process and get all of those molecules to stop reacting, or we run out of monomer. We run out of the stuff that is reacting in the first place. There is a phenomenon known as crosslinking. So if you can imagine the polymer molecules forming these long chains, crosslinking is the creation of bonds between the chains and each other, with the result being a more rigid structure as a result. Next week, you're going to do the Polymers Lab. You'll actually see the difference between the two. We will start you with a chain of polyvinyl acetate that we've dissolved with water. It's going to be kind of loose. It's basically Elmer's glue that we've added water to. So it's going to lose some of that stickiness. It's going to lose some of that viscosity. It's going to be kind of loose and flowy. But we're going to introduce a cross-linking agent to it. And when we introduce that cross-linking agent, it's going to cause the whole thing to seize up and make a semi-solid. So out of this soupy goo, we're going to get something solid because of cross-link action. Now the chains themselves, because they are kind of these flowy, loose strands, what we can see is that they can also interact with each other. They can fold on each other. They can loop on each other, make spirals. They can stack on each other. They can kind of intertwine with each other, depending upon the circumstances. So there are attractive forces between these molecules and themselves. And so because of those attractive forces, they will form other shapes. They will interact with each other. They don't have to just refer to cross-linking to strengthen their own bonds. So here we have an example of cross-linking. You can see that we've got several chains here. And we see that those chains are linked together with each other through those cross-links. Those cross-links are going to make those chains stronger by connecting them better. Okay, last thing I will talk about are the two means of polymerization, addition and condensation. So with addition polymers, what we are looking at is a repeating unit, a single repeating unit going over and over and over and over and over again. So the example here they give is polystyrene. Polystyrene comes from the monomer styrene, which is this guy. And what happens is that as the polymer grows, basically we can look at this double bond here and note that one of those bonds is going to leave and hook up to another styrene. And that'll hook up to another styrene. So that double bond just keeps moving on and on and on and on and on and on until we have thousands or hundreds of those styrenes linked up together. And so if we're looking at styrenes or if we're looking at any of these addition polymers, what we should be able to see is that there are notable repeating units that we can notice. So in this one, all of the units look the same. In this one, we can see that every second element on the bottom is a chlorine. So that's how the repeating units work there. Every second element is a CN molecule. Here, every repeating unit is 4 fluorine. Here's that polystyrene in it. So that's addition polymer. On Monday, we will start looking at the condensation polymer, and then we'll get right into examples and looking at some more specifics about kind of our common consumer products involving polymers. Have a good weekend.